Okay, so we're on to class 7 of ES211, and we're dealing with the kinetics of particles, and this is Newton's second law in both path and polar coordinates. We're in chapter 12, right? So we've actually, I believe that we're breaking down chapter 12 into subparts right here, I think. Yes, originally we had Newton's second law was just going to be section 12.1, and then we have section 12.2 was angular momentum and orbital motion. Section 12.3 was applications of central force motion. But I think we wanted to concentrate more on that part of section 12.1 and make it into two classes right here. So we did Newton's second law in rectangular coordinates, and now we're going to do it in path and polar. So the bottom line, and here we have the little section from the equation sheet where we have F equals ma. We broke it into x, y, and z in the previous class. Now we're going to break it into tangential and normal and radial and transverse, right? So where that acceleration was in the x direction, y direction, and z direction, now it's going to be the tangential direction, the normal direction, and radial direction, and transverse direction, right? So we're going to use those coordinates systems that we introduced in kinematics. We're going to use them in kinetics. This used to be two classes, but that was back when in kinematics, excuse me, we had the path and the polar as simply one class. So I broke it apart. All right, so you already saw a newt dog right here flying off of the roller coaster, right? So that's like going around that's like a tangential type of motion right there, because he would just keep flying off and going in the tangential direction. So, but we want to have forces that are going to draw him and bring him and capture him and bring him back in toward the onto the piece. Okay, so let me switch over to my document camera right here, and we will recall from kinematics when it comes to path coordinates right here. This is section it's called a D2. That's right in there. That we can break down the acceleration into the dv dt component right there in the tangential direction, and then the v squared over rho in the normal direction, right? So remember that we could think of this as at and think of this as an, right, in those components. So now on our free body diagram and inertial, I call it inertial response diagram. Often I'll call it the inertial body diagram, just because FBD and IBD kind of sound good together. But you could call this the inertial diagram, inertial response diagram, whatever you want right there. But so we draw the thing onto here, and we see that any of the forces, the sum of the forces in the tangential direction, are going to equal the sum of the the inertial forces, right? The mass times acceleration in the tangential direction, which is going to be down here, mass times acceleration in the tangential direction, or mass times dv dt. Remember, that's the change in speed, right? That's the idea here, is that tangential acceleration is only about the speed changing, the magnitude of the speed. And then when we have in the normal direction, we have the sum of the force in the normal direction, we have mass times acceleration in the normal direction. We know that that's going to be v squared over rho. And this is sort of like, this is because of the change in direction, right? The so-called centrifugal. And so this is actually the centrifugal force. And in terms of like when we actually hear people talk about that, that's the centrifugal force. And you're saying, well, doesn't that push to the outside? It's like, no, the centrifugal force is actually towards the inside. And it's hard to reconcile. So sometimes people will say the centrifugal force is an imaginary force, right? Well, let's say that you're in a car right here, right? And let's say that it's a Ford Mustang. 1 second, visual aids needed. This Ford Mustang, right? There's 1964 and a half, and you see there's a little skeleton dude inside there. See the little skeleton dude? See, he's inside the car. He's a little Lego skeleton dude. He fit in there. So you're that guy right here, and you're coming around, and let's say you're in a straightaway, moving along, and then then you start into the curve, right? And you know that you're accelerating into, you're accelerating towards the center of the thing, right? We know that we would just be going straight, but if we're going to turn to the left, having gone straight before, that means there is a change in velocity going left. So that means there's an acceleration coming left right there. But you, as a particle, want to keep on going. In fact, if you stop right here, poof, through the windshield, you will go, and you will keep on moving right here. You want to go straight, but the car is making you turn. The car is forcing you to accelerate to the outside. So you are leaning outwards because you want to keep on going. But it's the car that's pushing you to go towards the center, because the car is definitely accelerating that way. You want to keep going in the direction you are. So the car's forcing you to accelerate you into that direction. So what you're feeling is a force of the car pushing you towards the center of curvature. And that's the imaginary force. You think you're being forced outside. No, you're just going to keep on going where you were going. It's the car is forcing you towards the inside. And that's why it's an imaginary force, because we have this sense that we're being forced to the outside. No, because we're a particle. We are the skeleton that's inside this. And, so we're the Lego skeleton. And oh, there he just lost his legs. That's tragic. That's tragic. Oh, because he's hanging on. He's hanging on to the. Yeah. Oh, and I think I removed the seats in here just so that he could be in there. And now I'm ruining the whole thing. Yeah. I don't even know how. I might even have put him in there by. Yeah. So anyway, this is where we're using Lego skeletons for a reason. I think this came with a pirate set my son had right here for the Lego skeleton. So that was a good use of that. But I saw these cars at a CVS. There was a display at the CVS where they had all these toys, and there was like 3 of these black Mustangs, and I want this black Mustang. I want that, except I'd have seats in mine. And let's see, that it's a 1964 and a half. That was the first year of the Ford Mustang, right in there. But I would take one that was anywhere 65, 66, 67, even a 68. I don't really want a 69. I had a 69 in high school. It was a beat-up car. I bought it for like $450, and it was worth that $450. It was not a very good car, but I'm gonna force the skeleton back in there. All right. So anyway, I digress. This is now. So here's an example. We'll do this example and make a break, and then do another one. Okay. So we have the Dukes of Hazzard right here, and it's supposed to be funny because it's the Dukes of Hazzard, but doesn't age well. Confederate flag on the top of it, but it was a stupid show, so it was kind of funny in that sense. During a high-speed chase, a 1,100 kilogram sports car, the Duke boys, the Dukes of Hazzard, traveling at a speed of 160 kilometers per hour, just loses contact with the road as it reaches the crest of a hill. Determine the radius of curvature of the vertical profile of the road at A. Using the value of this in part A, determine the force exerted on a 60 kilogram driver by the seat of his 1,400 kilogram car traveling at a constant speed of 80 kilograms passing over A, right? So there's two separate cars. One of them is going to be a bigger car. It's going to have a 70 kilogram driver in it. Okay, and so we convert this into meters per second and meters per second in both cases. And if you haven't seen the Dukes of Hazzard, you don't think this is funny at all. All right, so our always starting with the free body diagram. And so we're going to draw this car. And it's at the crest of the hill, so we're going to draw it like it's right up there. It doesn't hurt to make it a lifelike drawing. FBD, IBD. Okay. So what are the forces acting on this? Well, it loses contact with the road. So the only force that's happening onto this thing is the weight of this car, right? And if I was going to be accurate with my coordinate axis, this is the tangential direction, and that's the normal direction, right? We might even put an ET and an EN in there. I didn't. All right, so nothing is, we don't know that it's decelerating or anything. It's probably not, because there's nothing in the horizontal direction that would be force-wise, except maybe air resistance. And we can put them on there if we want to. So let's even put this right here. Let's just say this is the force of drag, FD, onto this right here. So we could say that maybe it is ever so slightly slowing down in that direction. But here, we're accelerating down here, right? So this is going to be mass times the acceleration in the normal direction, which is going to be mass times velocity squared over rho, right? That's what that is. So taking the sum of the forces in the normal direction is mass times acceleration in the normal direction. And here's where positive is according to us, right? So we go ahead and take this weight is going to be mass times gravity, right? So interestingly enough, mass times gravity is going to be equal to mass times velocity squared over rho, right? Only thing that's happening in what's the vertical direction in this scenario right here, mass cancels out. It didn't matter how much the car weighed. Wow, that doesn't seem like it makes sense, but it's right there. It's right built as part of that. So we got 9.81. It's going to be equal to the velocity of this thing, which was 44.44 squared, and it just loses it, right? So that's, this thing is just out of contact, right? I shouldn't even, don't draw the ground in your free body diagram. And so we get this rho. So we get a rho that we find to be 201.3 meters. Interesting stuff, right? Now let's talk about the part B here, where we have with the same curvature. So it's the same hump, but it's a different car. And it turns out the car's not going to matter. We want to determine the force exerted on the 70 kilogram driver by the seat of this car. This is a red herring. We don't need this mass right here, but we do need the mass of the guy. So if we want to find the forces on the person, we have to draw the person, right? So let's draw the person right here, sitting right there, and he's smiling, right? And once again, here is the tangential and normal, and that's going to be equal, and let's try to draw the same drawing. I don't know why I gave him round feet, but unless I can make him go, wee, oh, amazing, okay. And he did, his arms fell apart. Okay, so once again, he's going to have a weight, right? Let's make the weight down this way. Here's the weight of the guy, right? But we also have a force being supported right in there. So this is going to be the thing we were looking for when it came up here, right? This is the force exerted on the driver right here. And okay, so but here again is going to be the mass times the acceleration in the normal direction that's happening to him. And I'm going to ignore what's happening in the horizontal direction. We don't know if the car is probably slowing down. So that would be an acceleration coming this way right here, so he'd actually probably have to be holding on to the steering wheel because the seat can't. Oh, well, that could be the seat belt, maybe, is pushing him onto there if he's slowing down. So anyway, we take the sum of the forces in the normal direction equals mass times acceleration in the normal direction. Here is what the positive is going to be. We know it's going to be the weight of the dude, right, minus the force n. And this is negative because we decided that downwards was positive. And it's going to be mass times the velocity of him divided by that. Right, so in this case, it's going to be the dude, and the dude is 70 kilograms, and his weight is 70 kilograms times 9.81, so there's it is in newtons. Here's the thing we want to get. We're going to take the 70 kilogram dude. Now he's traveling at 80 kilometers per hour, so he's at 22.22 squared right here, and here is the radius of curvature. So we're going to find that the normal force that the guy feels is 515 newtons coming upwards, right? That's the force of the seat on him. But you should recognize as part of this right here, you are typically, I almost said normally, and that would be like a pun. So I would say typically he would feel 686.7 newtons, right? So by coming over, he feels almost like he's lighter all of a sudden because he's going up over this hill, right? So therefore he is feeling much lighter otherwise because he's not pressing. All right, so there you go. There is that part of the video in 16 minutes, and we got to play with our toy car and our little skeleton right there. And look at the detail right there. Look at the little decal. Isn't that nice? Oh, I want this car. But I want my car to have better lines than this. Look at that. It's not that good. The fit and finish. It's typical. Mustangs aren't really all that great cars, but I like them. I like the way they look. Cool.